Here I begin another very essential derivation of physics, where I'm going to derive a very familiar equation of kinematics. But unlike my derivation where I used algebra to do this demonstration, in this case I'm going to use calculus. So in some ways you could look at them and say that they're equivalent and that they get you to the same final end. But the calculus presentation is more general because the calculus technique that I'm going to apply in getting to my final answer applies in vastly more cases than the algebraic version does. So I'll make a start here. What I'm going to do is begin by asserting that the kind of problem that I want to solve is problems of motion with constant acceleration. So my derivation begins here with the assertion that the acceleration is a constant, and I proceed from there. I recall that the acceleration is defined in terms of a derivative, that is an instantaneous rate of change. It's the derivative of the velocity with respect to time. And this is where my derivation starts, because what I'm going to do is appreciate the fact that the fraction that appears on the right-hand side, dv dt, is just that. It is in fact a fraction, and I can algebraically manipulate it. So what I'm going to do is solve that for dv, the differential of velocity. It gives me sort of a curious looking equation here, but one that if I read it makes an awful lot of sense. An infinitesimal change in velocity occurs when a constant acceleration acts for an infinitesimal amount of time dt. So I have a certain constant acceleration, I let a little bit of time expire, and it changes my velocity a tiny little bit. This expression is certainly true, but talking about it in the context of infinitesimally small changes doesn't really do me a lot of good. I want to know what is the entire change. And so to get the entire change, that's what I'm doing when I invoke calculus. The integral sign is essentially a big S that means add up all of the infinitesimal changes. That is, I'm going to add up all of the infinitesimal changes that occur in dv when the acceleration acts over time. Well, naturally, if I add up all of the infinitesimal changes, what I get is the entire change. This is a powerful equation that I've written just here, that the integral of the differential of velocity yields the change in velocity. This thinking is what drives most of my applications of calculus to the doing of physics. But the dv appears on the left-hand side of the equation. What I need to do, what is critically important and gives me the most information, is to integrate the right-hand sides. That is, I have to integrate the acceleration dt. Now, once I learn a little bit of calculus, that integral is an easy one to perform because it requires that I apply the power rule. Since the acceleration is a constant, when I integrate it, the integral of a dt simply becomes the acceleration times t. And that is the end of my derivation. But all the way over on my right-hand side, I had that the acceleration times t would be equal to the change in the velocity. Any change quantity, like here delta v, would be equal to the final velocity minus the initial velocity. That's how I define changes in physics. Well, with a little bit of algebra here, I get sort of a side result that's very familiar, and that is that the final velocity is equal to the initial velocity, a times t. This is familiar to me because not only is it the definition of acceleration when you stir it around, but also it's an equation that I use to find the final velocity when I'm solving problems of motion with constant acceleration. I'm not done my derivation though, because this quantity that I have on the left-hand side here, v, is not the velocity on average. It is the instantaneous velocity. It's the velocity at a particular instant in time. This equation gives me that. You tell me a time, I'll tell you what the velocity is. So I remember back to how I define this instantaneous velocity v as the rate of change of position with respect to time, dx dt. That is how velocity is defined. Well, I'm going to proceed doing the same sort of calculus here, which is part of what makes this such a good exercise. And I'm going to rearrange that to solve for the differential of position. That is, an infinitesimal bit of change, dx, is equal to the velocity dt. This is going to be a bit more sophisticated because I know what the velocity is equal to, and so I'll be plugging that in. But proceeding with the same pattern that I did before, what I'm going to do is add up all of the changes in position. And what that'll get me is the entire change in position. You see the similarity between what I've written up here. The integral of dv is equal to delta v, and down here, the integral of dx is equal to delta x. And so I'll have to integrate the right-hand sides, which means I'll be integrating v dt. A little bit more sophisticated now because I know what v is equal to. To keep it clear, I'm going to put parentheses. I wouldn't normally do that, but v is equal to v naught plus a times t, that quantity dt. Now I don't have to worry about dt is multiplying both terms in the quantity or any of that, because I'm very familiar with the operation of calculus, and I know that there's a rule that says that when I integrate a quantity that is a sum, the result is the sum of the integrals. So I could divide this into two integrals or however you like. The fact of the matter is v naught, the initial velocity, is a constant. And so when I integrate v naught, I get v naught times t as my result. The acceleration is multiplied by t here. So when I apply the power rule to that integration, I'm going to promote the exponent. That is, it'll be a times t squared. But I also divide by the promoted exponent, and that's what gets me a factor of 1/2 out in front. v0t plus 1/2 at squared looks very familiar. If I appreciate that over here on the left-hand side I have delta x, which is x minus x naught, then I can write this as the very familiar equation. That delta x is equal to v0 times t plus 1/2, the acceleration multiplied by time squared. Delta x, of course, is x minus x naught, and so really the way we are most familiar with seeing this is x is equal to x naught plus v0 times t plus 1/2 a t squared. A very familiar physics equation derived with the artful application of calculus.